Good day, good day, good day, and welcome to the National Tutoring Campaign. This is Nonkululeko Madondo. I am your teacher for grade 11. Thank you, everybody that have just joined in the class. I hope if you are in the right class, this is your physical sciences for grade 11. And oh, guys, it's been a long week, okay? I hope that everybody has had a chance to do the first part of our electrical circuits. If you guys remember last week, we were doing mostly, the theory part on what is circuits, what is conductors, what is electric power. We did all the theory part. So how we divided it, like I mentioned on our previous class, that last week we did the theory part of it, so that this week we can do the more calculating part of it, seeing that it's a very vast chapter and it's got a lot of things that you guys have to understand, not only for the chapter, but for your test and for your exams too. So I hope that everybody has gone through the work and is ready to get into the more calculative parts of our subject. I'm just reminding you guys in this classroom, if you have questions, you can send on the chat box, and I will read out your question and then we can see. And please, guys, make sure you do not get stuck not knowing what to do, and you end up, getting confused. If you have a problem wherever I am, you just send a chat and I can try my best to just go back and explain what is happening. And another thing, we don't have a lot of house rules, but I love interactive people so that we know where we're going and where we're getting stuck, because at the end of the day, we want to get those A's for physical sciences grade 11, so that you can use all these marks to go and, apply for university endorsements, etc. So guys, thank you guys so much for joining me here. So just going through the overview, we're going to be doing some calculations on resistance and Ohm's law. We're going to do ohmic and non-ohmic conductors. Basically, we'll still be doing the calculations. We're going to do series parallel connections. And another part we didn't touch on last week, which is the internal batteries. And we're going to learn more about that because it's also part of your syllabus. And we're going to do some energy in an electric circuit. I'm reminding you guys once again that here, we work on the Siyavula textbook. So if you do have the Siyavula textbook, it's highly recommended because it's a standard one that it's easy for you guys to be able to download, and it's also CAPS approved. So it's a good textbook that you can use, especially if you want to understand some of the work, and it's well explained. So, but any other textbook that you're using, it's fine. As long as it's grade 11, we're all doing the same syllabus. So it should be worth understanding. So you remember last week, we went through the basic concepts of a conductor, ohmic conductors and non-ohmic conductors. We mentioned that ohmic conductors have a constant resistance when the voltage is varied across them, or the current through them is increased. A graph of the current versus voltage. We've already done that on our previous lesson. And we said that our examples is resistor. Sorry, this should be an S. It's a resistor and nichrome wire. And we also mentioned non-ohmic conductors. Resistance changes as their temperature change. Remember, guys, we explained this that the ohmic conductors, they obey the Ohm's law. So which means that the temperature at constant temperature, okay. And then for non-ohmic conductors, the temperature change. So you'll roughly not be able to use your Ohm law. Okay. So the summary of the electric circuit, just going back for the overview. Number one, we can start on this graph here, on this column here. It says the current is a total charge that passes through a conductor per unit time. Okay. So this is our current equation. Okay. So this, guys, you'll usually use this equation if they give you, for example, they give you a charge and they give you a change in time, for example, at so and so seconds. So this is when you would likely be able to use this equation. So it will be measured in amps, in amperes. And then the EMF or potential difference, in this case, guys, we're talking about the voltage. Just know that all the time. Then we talk about EMF and potential difference. We are actually talking about the voltage, basically. That's the potential difference. So here the work done, energy transferred per unit charge to move charge from negative electrode to the positive electrode in a battery. So the potential difference is the work done per unit charge between 2 points in a circuit. Okay, so that's why you see all the time, if we're measuring voltage, we'll put 1 point here and another point there. So that's what it means, between 2 points in a circuit. So this would be our V is equals to work done times our charge, and this will be measured in volts. And then we move on to our resistors. Guys, you know the resistor is a very big chapter, because we sometimes have to do our series calculations. Sometimes we have to do our parallel connection. Can you please mute your mic? Okay. So there's a difference. Whenever you do an electrical circuit calculation, there's always a difference. Because at the end of the day, they might ask you to calculate the voltage, they might ask you to calculate the current, they might ask you to calculate the work done, or they can ask you to calculate the power or the energy. So what's tricky here when it comes to these two circuits is that these circuits are different. Okay, these circuits are different. Whenever there's resistors in series like this arrangement that you have, this will be your battery, but usually, you know, we'll have it like this. It will be just 2 lines, but here I just put a battery so that you know that this is where the source of the whole circuit comes from. So here, if you have resistors in series, like we mentioned last week, that our R total will be R1 plus R2 plus R3. Okay, so once you get this right, you'll be able to get correct answers with all of them. But the minute you make your mistakes with the R total, then almost your entire calculation or your entire problems in the questions is going to be wrong, because you're going to need your resistance to calculate your current, and you're also going to need your resistance to calculate your voltage. Okay. And then when we're in a parallel arrangement, like we mentioned last week, is that here, how you calculate it is going to be your R total will be equals to 1 over R1, 1 over R plus 1 over R2 plus 1 over R3, and then you're going to find the common denominator and get your answers. Okay, so in a parallel circuit, your voltages, if they give you, for example, the voltage here is 10 ohms, it means that it's going to be 10 ohms for all of them, because for a parallel circuit, voltage is the same across all points. Okay, but your total current is going to be divided. So why is it going to be divided? Because your current is going to start here, and some of it is going to split here and split there and split there. So that's why they call a parallel circuit a current divider. But on your series circuit, our current, we've got a voltage divider, because our voltage, remember, it's across. So it's going to be V1 plus V2 plus V3. So our series circuit is a voltage divider. Okay, but our current is going to be the same in all the points, because it travels from this side all the way to that side, and it doesn't split anyway. Okay, so going back to our Ohm's law, the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. This is always your keyword, guys. The constant temperature is what is most important when it comes to the Ohm's law, because the minute, if they say, for example, the current has changed, the temperature has changed from 1 to 10, can you still apply the Ohm's law? What do you guys think? Will you still be able to apply the Ohm's law if your conductor, if your conductor temperature changes? Does anybody know? If anybody knows, they can just send on the chat. If your temperature changes, does Ohm's law still apply? Anyone? Okay, no, it doesn't apply, guys, because Ohm's law is only respected when the potential difference across a conductor will be directly proportional if the conductor temperature is at constant. Okay, and then now we're going to explain a bit about the energy used by a component. Energy in this case will be the work done. Okay, so the general equation for work done is going to be work is equals to voltage times current times time. Okay, so if it was power, it was just going to be V times I, but because it's work done, it's voltage times current at a specific time. Okay, and then for series, this is how you'll have your calculation. Your W will be equals to I squared R times T. But for your parallel, I'm going to say work done is equals to V squared over R times T. Okay. Okay. So the energy used by the component, that's how the calculations are going to be done. And then for the power, because we've got work done and we also have power, it's in this case, it's the rate of which electrical work is done or electrical energy is transferred. Okay, so that is how we calculate our power. And our power is going to be work done divided by change in time. So that's going to be our power equations. And P is also equals to VI, like I mentioned before, that the difference between the work done here and the power it's here. Okay, here it's VI times T, and this one is just V times I. Okay, are we together, guys? Hope everybody's following. If you're getting confused, please do ask, guys. This should be an interactive class and we should all have an understanding. So now, still going on to the summary of electric circuits, we said that our Ohm's law states that voltage is equals to current times resistance. So this is a small triangle that you can also do for yourself when you are working for when you're in your exams or in your tests and you want to remember how your Ohm's law works. So this is a triangle that you can use, and you can put your V and your I and your R there. The V will stand for voltage and I for current and R for ohms. Okay, I mean resistance, which is in ohms. So what you can do, you'll be able, this triangle helps a lot, because if, for example, you want to calculate your current, you can say your current is equals to V over R. Okay, because I know sometimes you can mix the two up and not be sure if you're dividing the resistance or you're dividing the current, etc. So this is how you would calculate it. And then if you had to say calculate your resistance would be your voltage divided by current. And what would be your voltage? Your voltage will be equals to current times resistance. Do you see how simple this is, guys? This is just a simple way on how you can try and find your equations without struggling too much. Okay, there you have it there as well in these triangles. This is how you would do it. So now we're going to the equivalent circuits. Remember last week we spoke about series resistance and its characteristics. So today I'm going to be using an example to try and explain the equivalent series resistance. So let's do this example here. It says on this example, two 10 kilo ohms resistors are connected in series. So you already know when they're connected in series, it means that it's going to be one circuit and you're going to have your three resistances there. So here they want you to calculate the equivalent resistance. What is an equivalent resistance? Equivalent resistance is a single resistance representing all the entire resistance of your circuit. Okay, so that's what an equivalent resistance is. So if they wanted to calculate the equivalent resistance, is another word for total resistance. Okay, so how are we going to find our equivalent resistance? We're going to say R series, because they are in series, is equals to R1 plus R2 plus R3. And therefore, it's going to be, you're going to substitute what you have there, and that's going to give us 18 ohms. Looks simple, right? Yeah, there's not much of a problem when you're dealing with series resistance. So they say determine how you approach the problem. Since the resistors are in series, Rs is equals to R1 plus R2. And for example, in this case, if you have two resistors, you'll just add them together and they'll give you 20 kilo ohms. Okay. So okay. Okay, I put this slide on a wrong place. Okay, let's start with this one first. It says, now we're going to be I'm going to be showing you guys the equivalent parallel resistance. Remember, now we just did the series resistance. Now we move on to the more complex one, which is the resistance, which is the parallel branch. It says that two 10 kilo ohms resistors are connected in series. Calculate the equivalent resistance. Okay, so what do we want? We want to find basically the minute they say equivalent resistance, you want the total resistance of the entire circuit. So you're not going to put them one by one. You have to add them together. But because these ones are in parallel, remember we're using the parallel equation. And don't forget, guys, I've seen other students, they tend to forget and they just write RP over here. And then they say it's equals to 1 over R1 plus 1 over R2 plus 1 over R3. Do not forget to put this one as 1 over RP as well, okay? Otherwise, your answer is going to be wrong. Then you're gonna substitute your R's as stipulated here. It's going to be 10. We've got 10, we've got 2, and we've got 1. So now what do? We look for our lowest common denominator here, and it's going to be our 10. So we put a 1 there because 1 times 10 is 1, and 2 times 10 divided by 2 is going to be 5, which is this one, and 1 times 10 is going to give us a 10, and we can have it there as our 10, and this will give us our 1 over RP. Okay, so this is an answer for 1 over RP. You'll be able to see that that answer 1 over RP is not the same as RP here. So what do you do thereafter? You're just going to swap them around. So basically you're trying to make RP the subject of the formula. So you're going to swap this. You're going to say 10 divided by 16. That's going to be giving you the final answer for your R parallel. I don't know if you guys understand. If you're getting stuck, just let me know and I'll re-explain it again. So here's another one. It says 2 ohmic resistors R1 and R2 are connected in series with the cell. Find the resistance of R2. So what are we looking for? Okay, here, given the current flow through R1 and R2 is 0.25 amps, and that the voltage across the cell is 1.5 ohms, and R1 in this case is 1 ohm. So what do we do first? Whenever they give you a question and there's no diagram that's drawn, it's always a good idea for you guys to try and draw it so that you can, visualize the problem that you're working on, and it will be easier for you to see what is not given. So here, because they are series, so the current is going to be the same in both resistors, okay? Because why? Because this is a series circuit. So it's only the voltage that's going to be dividing. Okay. So we've got our R1 there, which is equals to 1, is our R2 there, which we do not know what it is, but we've got our current. Okay. So how? Oh my God. Resistance. Okay, I think I just mixed up some of the slides. Okay, so how are we going to do this? So now we're looking for this one. We can find the voltage here, right? So what are we going to, let's start with this one. What are we going to say here? I just don't have a pen here. Let me see if I can try and write something. Okay, so we're going to first start calculating the voltage here, right? We are looking for R2. So we're going to say V. Oh no, it's disappearing. Sorry about that, guys. Vanishing pane. Okay, so we're going to say V1 is equals to I times R. Okay, so it's going to be I times the R1. Okay, then once you get this total, you're going to take this total and you're going to say V total is equals to V1 plus V2. And then we're going to make V2 the subject of the formula. And then once we make V2 the subject of the formula, it's going to be V total minus V1. Okay. And then after that, once you have V2, then you can be able to find your R2, because you're just going to say R2 is equals to V divided by I. And then that's how you find your answer. I don't know if it makes sense. If you guys want me to repeat it, I can do that. But that's how we would calculate a problem of this nature. Okay. Any question, guys? Okay. So I want us to go back to this problem here. I just put it before the other questions, but this one is our parallel equivalent circuit. This is how a parallel equivalent circuit would look like, right? You would have your two series branches, and you also have a parallel branch. Okay, so these two are in parallel and they're in series to this one, just by looking at it, because you see the nodes here, these nodes here, it shows. Okay, so but you guys are going to see how we're going to do it, because we still also have this one. So these ones, we're going to have to calculate the parallel circuit and the series circuit all together. And this one is also in series once again. Okay. So, but let's see how we're going to work it out. It says in the circuit diagram below, resistance of a battery, wires, and ammeters are negligible. So once they say that the resistance of a battery is negligible, it means that we won't be calculating internal resistance. So the EMF of the battery is 30 volts, as you can see on the diagram. They want us to calculate the reading of the ammeter. So basically, this is the ammeter. Like I mentioned to you guys, an ammeter is a meter or an instrument that is able to calculate the current of a circuit or any point where you put it. So basically, it's just a representative of the current flow, and it gives you the value in ohms. So now we've got the ammeter right here. So now we're going to, before we even do this, we're going to have to start by making our resistors an equivalent resistance. Okay, so we need one representation of our resistance in order for us to find the total current. Okay, so we come here. So now, as you guys can see, we try to put it in a way that we can be able to see what is what and where is what going. Okay, so you always start from the nodes. You always check the nodes. Okay, you always check the nodes on how things are connected, and this is how our diagram would look like. This is a diagram here, but now just by looking at the nodes, we try to fix it in a way so that we can be able to see how they are positioned. So now we've got a parallel branch here that is in series with R1, but these two branches are also parallel to R4. So what are we going to do first? The first thing we need to do, we need to make an equivalent resistance for R2 and R3. And how are we going to do that? Because this is a parallel branch, we're going to have to use the R parallel equation. So we're going to say 1 over R2 and 3, R2 and R3 is equals to 1 over R2 plus 1 over R3. And therefore, because each of them, they said it's 10 ohms, we're going to put our 10 ohms there. Okay. So because this is going to be, so here it's going to be 2 over 10, but now swapping them around so that we can make the R23 the subject of the formula, they're going to swap and it's going to be 10 over 2. And that 10 over 2 is going to give us a final value of 5 ohms. Don't forget, guys, to always fix this side of your resistance so that you do not get confused. And then R1 and R23, Remember these ones now? Now we've got an equivalent circuit here, one block. So we can say now for this series branch, we're going to say R23 plus R1, and that is going to give us 15 ohms. Okay. Guys, I hope everybody's following. If you're not following, just tell me so that I can go back and explain where you guys are getting confused. So now you've got two branches, which means here you've got your 15 ohms branch and you've got your R4 as well. So now you're going to have to do another parallel equation for you to find the equivalent resistance. So here we're going to call it R123 because now they are all compacted into one. So R123 is equals to 1 over R123 plus 1 over R4. So we can just call this the R equivalent. Okay, we don't have to call it 1, 2, 3. You can call it R equivalent because our R123 is the parallel branch of R4. And then 1 over R23 is equals to 1 over 15 plus 1 over 15 because our R4 is given as 15 as well. So our R23, don't forget to swap it around because here it's going to be 2 over 15 and then you're going to swap it. It's going to be 15 over 2 and this is going to give you 7.5 ohms. Okay. I hope we're still together and you guys are still following. So now we've got our equivalent resistance. So which means that now we've got our circuit as one block. There wouldn't be all these blocks. We're only going to have one block, which is our equivalent resistance. And then we can now calculate our current. Do you see how important the resistors are? The resistors are your baseline of all your calculations because you need to calculate using resistance to find current, to find voltage, to find power. You're going to use your resistance. So if you get it wrong, then everything is going to be wrong. So now we're looking for the current, the total current like they asked, and that's going to be V over R. And we already found our R is 7.5, and we know that our voltage is 30 volts. Okay, so now we can find our current, and that's going to be our 4 amperes. Okay, don't forget the units, guys. Without the units, your answer is totally wrong. So now we go back. It says I total is equals to I1 plus I4, and R123 is equals to 15 ohms. Let's see what's the next question. The next question, it says calculate the power dissipated by the 15 ohms resistor. So now they're looking for R4. Here's our R4 here. They want the power that is dissipated on your 15 ohms resistor. So that now you need to go back to your original circuit and try and find that. So this is going to be our circuit, how it looks like. So your current goes from this branch and this branch. Okay, so that's why it says I total is equals to R1 plus R4. Okay, I1 plus I4, because they divide when they get here and then they go back and come back as I total again. So our I total is equals to I1 plus I4. So remember that our R4 is equals to 15 ohms because it's given. So I1 is going to be equals to I4. Okay. Do you guys understand where that comes from? I1 is equals to I4. So in this case, it's going to be I total is equals to 2 times I1. And I1, because it's equals to I4, it's going to be our 2 amps. Okay. And then we move on. So now it says I1 plus I2. Let's just go back to the next question. It says on 1.3, how will the reading on the ammeter be affected if the switch is opened? Okay, if the switch is opened here, it means that there won't be power going through R4, okay? Because which means the circuit is going to close here. The current is going to go this way, all the way there, and come back through this way. So this one is going to be out because when the switch is open, there's no current flow in here. Okay. So I want us to quickly move. Guys, if there's anything where you're still getting stuck, you can just send on the chat box and we can discuss it quickly before we move on to the next section of work, which it says here, real batteries are made of material that are resistant to corrosion. Okay, that's why batteries take so long before they start to have corrosion. So this means that genuine batteries include internal resistance in addition to being potential difference source. So there must be an internal resistance within this battery in order for it, to resist things like corrosion or getting damaged easily. So this small r here, it represents our internal resistance. They say an actual battery can be represented as an EMF linked in series with a small resistor if the whole voltage source is referred to as the EMF. The battery's internal resistance is denoted by the small letter r, which is what we have here. So sometimes you'll find that in your exam or in your test, they ask you a question to calculate the internal resistance. But you saw in our previous question, they didn't mention that the internal resistance is ignored. So if it's not ignored, then you're going to have to calculate it. So how do we go about working out our internal resistance? It says the EMF of a battery is practically constant because it's only determined by the chemical process which turns chemical energy to electrical energy that is taking place inside the battery. Remember, the battery needs to start up, and because it's the source of the circuit. So the battery needs some sort of power to drive it into creating electric current, and therefore current is induced within the circuit. Okay, so as a result, we see that the voltage across the battery terminals is proportional to the current drawn by the load. Okay, because the EMF is constant, the voltage across terminals decreases as the current decreases, because remember, current and voltage is directly proportional to each other. The voltage equals the EMF only when the current is very little, according to the same logic. Okay, so which means that the voltage and the EMF, which is the electromotive force, which is the minimum voltage required for a battery to start in this case, that internal EMF, if the voltage is very low, then they can be equal to each other, but in most cases they are different. So suppose a battery has an EMF and internal resistance RR supplies a current through current II through an external load resistor RR. So we're using the double letters just to denote that now we're talking about internal parameters. Then the voltage drop across the load resistance is that supplied by the battery. So the V will be equals to I times R. Similarly, from Ohm's law, the voltage drop across the internal resistance will be the internal voltage, which is the EMF, is equals to I times the internal resistance. The voltage VV of the battery is related to the EMF and internal resistance by, so the EMF is equals to the voltage plus the I times R, which is the internal voltage. Do you guys understand what's happening here? So basically, what they mean here is that when you calculate the EMF, it's going to be the voltage of the whole circuit plus the internal voltage. Okay, so that's why you find there they've got V plus the internal one, which is I times R. So this is how you calculate your EMF. So when you have a test and they give you your internal resistance and they ask you to calculate the EMF, then you can be able to say EMF is equals to V, the voltage of the circuit, plus the internal voltage as well. And alternatively, if they give you the EMF, you can be able to find your internal resistance if you have your voltage of the circuit if they have given you the R. So the EMF of a battery is practically constant because it is only determined by the chemical processes taking place inside the battery. As a result, you can see the voltage across the battery terminals is proportional to the current drawn. So the voltage equals the EMF only when the current is very little, like we've already mentioned. So a critical value, which is IC, limits the maximum current that can be extracted from the battery. So when V is equals to 0 amps at an IC current, the equation then becomes this. So if you have your critical current, basically, because it's a critical value, IC, then this is what you're going to do. A critical current happens when your voltage is equals to 0. Okay, so it's sort of like a startup before you start up. When you want to calculate your critical current, it's going to be when you derive the formula, it's going to be 0 because our voltage is 0 is equals to the EMF minus the I critical times internal resistance, and the I critical times resistance is equals to the EMF. So the IC will be equals to the EMF divided by resistance. So I hope you guys can now see how the maximum current can be determined from the battery. It's not simple, guys. It's not difficult, guys. You just have to, remember all these equations and remember how some of them get derived. Okay. So what is the internal resistance of a battery? If the EMF, now we're coming here, the EMF is 12 volt and the voltage drop across the terminals is 10 volt. When a current of 4 flows in the circuit, when it is connected across the load. So now we're looking for the IR. We are looking for this one here, looking for this R. So what do we have? We have the EMF as 12. We've got the voltage as 10, and we've got the current as 4. And that you can take this one, it's going to be 22, and you divide it by 4, and it's going to give you 0.5, and that is our internal resistance in ohms. Okay, so the internal resistance is 0.5 ohms. Don't forget to put your ohms there because that's your standard unit, and without them you do not get marks. Okay, so before we get too far, I'd like us to get to our parallel series parallel network. You saw the example that we did, but I wanted to also broaden it up by showing you guys the steps on how to think critically when you are working with a parallel series circuit. So you see here, there's a parallel branch. There's a parallel branch there, and we've got a series branch on this one. So basically what we want to do, we want to only have one block. Okay, so what we have to do is that we're going to have to calculate the parallel circuit here and make it one block, calculate the parallel branch here and make it one block, and then you're going to have R parallel 1 plus R4 plus R parallel 1 plus R4 plus R parallel 2. Okay, so this is how we work about it. They say these circuits are really simple to construct since you can apply everything you've learned about series and parallel. So guys, it's always advisable when you work with a series parallel circuit, if there's visible parallel branches, that you calculate them first. Okay, you always calculate the parallel branches first. The only difference is that you do it in stages and not all at once. So this circuit in the figure is made up of 2 parallel sections, like I've already mentioned to you guys. So we can determine the equivalent resistance of the complete circuit of all resistance in the figure have a resistance of 10 ohms. So we assume that all the resistances have a resistance of 10. So the first one, we're going to start by calculating the parallel circuit 1. So which is this branch here, which is this branch over here.
we're going to start with that branch. And it says here the value of R parallel 1 is going to be 1 over R parallel 1 plus 1 over R parallel 2 and R parallel 3. And you're going to have your common denominator, which is 10, because they said all the resistances are 10. And here it's going to be 3 over 10, but then we're going to have to swap it around, and it's going to be 10 over 3, and this is going to give us 3.33 ohms. Okay, don't forget here, this one is a mistake. They're supposed to write 1 over R parallel, 1 over R parallel. Just write it all the time in steps so that you can remember that, oh my God, I forgot to swap them around. Because if you don't swap them around, you're going to get an incorrect answer, which means your current, therefore, is going to be incorrect. Your voltage is going to be incorrect. Your power is going to be incorrect. And everything is going to be a big mess, okay? And then after that, we're going to come to this one as well and calculate the branch. But because they are all 10 amps, this one is going to be equals to this one. But you have to do the steps in order for you to get the marks, okay? You have to do the steps. So now we've got two parallel branches. We've got R parallel 1, R parallel 2, and we also have our 4 ohms resistor. So this is what we wanted, okay? So that we can make it an equivalent resistance. So which means now we can say the R series is equals to R parallel 1 plus R4 plus R parallel 2. And this is what has been done here. So our lowest common denominator is going to be 30. And at the end of the day, remember, once you have the 230 over 30, you swap them around. You're going to say 30 divided by 230. And this is the answer that you're going to get. Oh, no, sorry, guys. We do not swap it here. This is the already in series. I'm thinking of parallel circuit. So here, it's just going to be the way it is because it's R. It's not a parallel now. It's a series branch. So it's going to be 230 divided by 30, and that's going to give us 7.66 ohms. Okay, you see how simple it is to do a series parallel circuit if you understand the steps on how to get your answer. So we're running out of time, but let me just see. Okay, so we're almost there. So now we're going to come to this one. Let me just fly through to it because we're almost running out of time. It says here, calculate the total resistance in the external circuit. And then they said, calculate the current in the 6 ohms, which is this one, resistor, and calculate the reading on the voltmeter V2. V2 is here, V2, okay? And calculate the energy dissipated, okay? So here, we're going to first start with our R parallel. We're going to start with this parallel branch. And then after you calculate the parallel branch, you're going to come and add it to your series branch. And that's going to be your total resistance of the external circuit, which is what we did here. We said R parallel, we found the answer. And then we said R total is 1.5 plus 3 ohms, okay? And after that, the current in the 6 ohms resistor, which is this one, the 6 ohms resistor. So the I total there is going to be V divided by R total. 10 divided by 4.5 is equals to 2.22 amps, okay? And then after that, you come to the parallel branch, which is the V3 here. You're going to say I totals times R parallel. And that is going to be your 2.22 times 1.5, and that's going to be 3.33 volts. Okay, so now you found your total current and you found your total voltage of the whole circuit. Okay, using the Ohm's law. So after that, now that we've got these totals, we can find our current for the 6 ohms resistance. And we know that parallel voltage is the same. Anyway, it's the same on top and it's the same at the bottom. So our VP, which is our 3.33 divided by the 6 ohms, that is over here. Okay, guys, this requires a lot of practice, and I hope that you guys are going to do more of these problems so that you do not, you know, go wrong on the exams. So now they say calculate the energy dissipated in the 2 ohms resistors in 2 minutes. So remember, guys, we did mention that energy always has time in it. So now it's going to be I squared R times the time. Okay, so in this case, our current is the 0.56 on the 6 ohms resistor. Now we're not using the total current, you're just using the 6 ohms resistor current. You see how everything is interconnected. And then our R is going to be the 6, and our total time is going to be 120 because they said 2 minutes. And 2 minutes, you know, our units is 60 seconds. So 1 minute is 60 seconds, 2 minutes is 120 seconds. And this is what we'll have. Other equations could be used also, which is power, which is equals to V times I. That would be 10 times 2.22. And 2.22 would be your total current, and your voltage will be your voltage, the 10 volts. Okay, and that would give us 22.2 watts. Okay, you use the total voltage over here. That's where the 10 volts come from. You don't use a parallel. So this is the power dissipated there. So you see the answers must be the same for it to be true. Guys, thank you guys so much for this class, and thanks for your patience. I mean, we've gone a bit overboard with time, but what can we say? You know, it's physical science and the work is too much, but we need to make sure that everybody understands. Guys, my name is Nonkululeko Matondo. I am your physical sciences teacher. You can get me on email, which will be sent to the chat. And I hope that if you guys have problems with any other section, if, for example, in your class, you guys are still doing different work, you can still get me on the chat and just find out how I can help you. I'm always there for you guys. I know that during this time, it's very difficult because most of the work that you guys have to do, have to study on your own. But I am here and you can get me. I've sent my email on the chat. You can ask me and we can do some more physical sciences. Thank you guys so much for the class and goodbye.